So in this video, we will understand the next part, that is the Nyquist plot. So the Nyquist plot is an extension of polar plot. So it is an extension or an example of polar plot. It is an extension or example of polar plot. So to understand the Nyquist plot, there are two important rules or the concepts that we need to understand. The first one is the mapping, and the second one is the principle of argument. Principle of argument. So your Nyquist plot is based on these two concepts. So these two, the mapping and the principle of argument, are the foundation of the Nyquist plot. Okay. So first we will understand the mapping. So for that, consider a characteristic equation. A characteristic equation. D of S is equal to 1 plus G of S into H of S. This is a characteristic equation. Now, S here, the S is a complex number. It is a complex number which will have both real and imaginary part. That is sigma plus J omega. Sigma plus J omega, where sigma is the real part, omega is the imaginary part. The plot between sigma versus J omega is nothing but our S plane. So you have, this is the plot. It is between sigma and J omega. So this is nothing but S plane. Similarly, now when we substitute S in, so S is equal to sigma plus J omega in D of S, the resultant, when you substitute it and simplify the equation, the resultant will be again a complex number. So obvious, S is a complex number, so D of S will also be a complex number or a complex value. Okay, so I'll write it as complex value. So now this D of S will be of the form U plus JV. So the D of S will be a complex value. So it will have a real part and an imaginary part, which is given by U plus JV. Now this plot between U versus JV, this is our D of S plane. This is D of S plane. So now when we plot it here, so y-axis, x-axis. The x-axis is U and this is JV. This is nothing but D of S plane. This is D of S plane. Now we will understand the mapping with a small example. So we will take a small example. Now I'll take, for example, I'll take D of S, that is 1 plus G of S into H of S is equal to S plus 2 divided by S plus 3. So this is one function I have taken. This is an example. Now S D of S. Now first I'll take S is equal to minus 1 plus J 0. So when I put minus 1 plus J0 in D of S equation, my resultant answer will be 0.5 plus J0. So when you substitute here, so minus 1 plus J0 plus 2 divided by minus 1 plus J0 plus 3. This is your substitution. So what you get is 0.4 plus J0. Then I take S to be minus 1 minus J1. Minus 1 minus J1. So when I substitute here, minus 1 minus J1 plus 2 divided by minus 1 minus J1 plus 3. So what I get is 0.6 minus 0.2 J or minus zero point 0.2. Similarly, next I'll take minus 2 plus J0. When I substitute in D of S, I'll get 0 plus J0. So if I take minus 2 minus J2 and I substitute in D of S, I'll get 0.8 minus 0.4 minus 0.4 J. So now we will plot the S play and D of S play. This is my D of S play and this is S play. Sigma J omega U JB. Okay, so first if we take minus 1 plus J0, I'll plot minus 1 plus J0 on the S plane. So this is where I'll take this to be S1, S2, S3 and S4. This is D1, D2, D3 and D4. So S1 is here, that is minus 1 plus J0. Now corresponding to this S1, we have a D1 number, that is 0.5 plus J0 in D of S plane. So this will be somewhere here. This is D1. Similarly, S2 is minus 1 plus J1. So this is S2. Now corresponding to this, we will have 0.6 minus J 0.2 in the D2 plane. So it will be somewhere here. This is D2. Similarly, D3 is minus 2 plus J0. So this is S3. So here it is 0. So this is D3. Similarly, minus 2 minus J2. So this is S4. And here I'll have 0.8. Sorry, coming to the D2. D2 is not located here. So D2 is located at this side. It's located in the fourth quadrant. So this is D2. So coming to D4, 0.8 minus J 0.4. So here is D. So you can see that for every point in S1, there is one unique point in D of S plane. So for every point here, there is one unique point in D1. Similarly, for S2, there is one unique point D2. For S3, there is one unique point D3. And for S4, there is one unique point D4. So this is called as mapping. This process is called as mapping. So we take a point in S plane. That uh, point will be mapped to D of S plane. So that is the uh, first concept here, where we do the mapping between the numbers. So you take D of S as some polynomial. It is a S-plane polynomial. Now that S-plane polynomial will be mapped into the D of S plane. So we can write every point. We can write here. So every point in the S plane, in the S plane, maps into one and only one point, one and only one point in D of S plane. D of S plane. So if you take a close counter, so like if I take here, so just remove this. So if I take a close counter like this is the close counter. So each point on the counter is some, like this is S1, this is S2. Okay, now this each point on the counter will corresponding to some other point on D of S plane, and that will also give rise to a counter. It's some arbitrary counter. Okay, so you take in the normal, in the clockwise direction, sorry, in the anti-clockwise direction, I've taken a counter. So every point is mapped into D of S plane. The resultant will be also a closed counter in the clockwise direction. The clockwise or the anti-clockwise direction. So the direction is dependent on the pole and zero that we will see in the next section. So here, so every closed counter in the S plane will be mapped to a closed counter in the D of S plane. So I can write any closed contour in S plane, maps into the closed contour in D of S plane. These are the properties of, so whatever we have mentioned, these two, these are the properties of mapping. This is the first concept where we have discussed the properties of the mapping. Now, this property of the mapping will be applied to get the principle of argument. So that we will see it in the next video. Thank you.